Alright, this video is going to discuss Chapter 3, Resistance. Alright, so looking at figure 3.1 in the book, this is from the Boylestad book here. This is the symbol of a resistor. A resistor is a two-terminal device, and it doesn't matter which way you would connect it, either direction. Current can flow either direction equally through an ordinary resistor. Okay, this is a fixed resistor. They also have three-terminal devices, which are variable resistors. We'll discuss those at a later time. But looking in section 3.2, we discuss where resistance comes from. So resistance is actually made, the resistance of a material is due to the physics of the material. So there's basically four properties of that material that define what the resistivity of it is. The first one, of course, is simply the type of material. So given the type of material, will determine to a large degree what the resistivity of that material will be. So here we have the Greek symbol rho. Okay, so this is the Greek symbol rho, and this is used to represent the resistivity of the given type of material. Now, the resistivity is based on the cross-sectional area divided by the feet given at a fixed temperature. So the units of the resistivity is, in this case, it's listed here as circular mils, which we'll discuss that's for like round wire. We'll look at that in a bit, but it could just be a cross-sectional area if it was a rectangular sort of shape. But so it's the area times the unit of ohms. So this is the Greek symbol omega, capital Omega, which we use to represent resistance, divided by feet. That's the length of the resistance. So if you look at this, this is the general equation for resistance due to the physical properties of the resistor. So we see here we have the resistivity, which has units of area times ohms divided by length. And then we multiply that times the length. So here we have the length in the numerator, and the units of the resistivity have the length in the denominator, and that way that they would cancel out. Those would cancel out when you do that multiplication. Okay. Similarly, the area, we divide by the cross-sectional area. And since the resistivity rho has that area in there, it's in the numerator, again, those would cancel out. Alright, now notice that the resistivity here is given at a fixed temperature. So the one of the fourth item actually up here on the list is the fact the temperature of the material. So the temperature of the material will affect how much resistance there is. So the and so we have here the length and the cross-sectional area. So as the current has to move through material, the longer the material is, obviously the more resistance there will be. That's why the length is on the top, and the cross-sectional area is in the denominator, because if it has more area to move, more electrons will be able to move through side by side. So the larger the area, the easier it is for those electrons to move through the material. Now, when we start talking about the cross-sectional area, okay, we're going to look at where the area is going to pass. Now, most wire is circular, and so if we look at using the American wire gauge, its ratings are given in circular mils. Right? So circular mils, 1 mil here is 1/1000th of an inch. Okay, and so a square mil would be 1 mil times 1 mil, and it would be a perfect square. However, if we look at this, right, we see if it's circular, these areas I'm marking over here in green would not exist in a circular wire then. So if we have a circular wire that has a diameter of 1 mil, then these kind of corner sections here aren't going to be in that wire, so that it's going to be smaller than a standard square mil. So if we look at the equation for standard square mil, for a square mil, so we see here that we have 1 circular mil is equal to pi divided by 4 square mils. And again, the reason for that is the fact that a true square mil is going to include these corners here, but a circular mil does not. So it's basically about 3/4. Remember, pi is 3.14, so it's about 3/4 of a square mil. But when you look at the wire gauge, okay, so if we look at the equation for a wire gauge, okay, for the AWG is the American wire gauge. And so you see here the area is given in circular mils. Okay? And at the fixed temperature, they give it to us the resistivity in terms of ohms per 1,000 feet. Okay? So, and this is assuming copper wire here. But the American wire gauge, we have 4/0 wire, or 3/0 wire, 2/0 wire, okay? And as the number starts going up, we see that the cross-sectional area goes down. Okay. All right. So like for typical automotive applications, you'll see we use a lot of times for straight wiring for lights and stuff like that, they would use like 16 gauge wire. So it would be 2,582.9 circular mils. All right. So here's a chart. This is table 3.1 in your book. And this chart is showing the amount of resistivity for some common materials. And so if you notice here, actually silver has the smallest resistivity, meaning that for the given for the exact same size, silver would have less resistance than copper or gold or any of the other items listed here. Second on this list you see is copper. So copper has a fairly small amount of resistivity. Okay, it's even better at conducting. This is basically resistivity. A small resistivity says that you are good at conducting electricity. So the smaller this number is, the easier it is to push those electrons through this material. All right, so you may notice aluminum. A lot of your transmission line wires especially are made out of aluminum. Okay, they're made out of aluminum because aluminum is light and it is very abundant material, but it has almost twice as much resistivity as copper does. All right, so given these, and again, remember that the resistivity is given at a temperature of 20 to 20 degrees. Now, certain materials, as the temperature changes, it's going to affect the type, the amount of resistance. All right, so if you look here, this is again right out of the book here. For conductors, as you increase the temperature, the resistance will increase. Okay, so this is saying that it has a positive temperature coefficient, so that as it gets hotter, you get more resistance. So copper wire, any of your copper wiring, as you run current through there and you heat up those wires, they actually have their resistance of those wires is going to heat up. Semiconductor type materials, on the other hand, as they heat up, they will result in a decrease in resistance, and that's referred to as the negative temperature coefficient. So as the temperature goes up, the resistance actually goes down. Okay, and that's also true for insulators. So as insulators heat up, they don't insulate quite so well. So just to be clear, conductor means that it's a material that easily conducts electricity. An insulator means it's a material that does not conduct electricity easily. It has a very high resistance. However, it can conduct electricity. It just doesn't conduct it very well. It just has a very high resistance. And semiconductors then are somewhere there in the middle. All right, this is figure 3.3 in your book, and it just kind of goes along with the equation for resistance. Now remember that the actual resistance comes from the physics of the material. So if you have two pieces of material that are identical in size, then their resistance is based on their resistivity. So if they have a higher resistivity, that means they're going to have more resistance for the exact same size of two materials. So we see again up here in this chart, we see that iron has a resistivity of 74, so it has a lot more resistance than copper does. If we look at the length, so here we have an example of, we have two pieces of wire that are both made of copper, but one has a much longer length than the other. So as the length increases, the resistance is going to increase. And then here we see that the area, this cross-sectional area, all right, the R1 is larger in diameter than R2. And so therefore, R2 has more resistance than R1, because R1 has more pathway for more electrons to move through simultaneously. So these are the three main factors assuming a constant temperature. So again, the equation for resistance due to the physical properties of the material is rho, the resistivity, times the length, divided by the cross-sectional area of the material. And so, and you have to be careful when you're doing these calculations. Like when you look up rho, when you're looking up the resistivity, look at the units that you're using. So the book typically is using circular mils because it's talking about wire in terms of American wire gauge sizes. And so it's circular mils, which is in inches, and feet, okay? But if you're looking, if you're searching Google to find the resistivity chart, you have to make sure, because you may run across a metric chart. And so in that case, then your cross-sectional area would be something like meters squared or millimeters squared, and your length would be in meters. So you need to make sure that when you are doing these calculations that you match your units. So if you're doing circular mils, it must be circular mils. If it's a rectangular form, then it's mils, and you have to use the equation to switch between them. So let me write that down here. So remember that 1 circular mil, 1 cm, 1 circular mil is equal to pi divided by 4 times a square mil. Okay, so if you're dealing with a rectangular material, but your chart is using circular mils, you'll have to do this conversion to convert the rectangular cross-sectional area into circular mils. Otherwise, you will be off a little bit. So make sure that you're using the correct units.